Okay, go ahead. Well, look forward to your teaching.
Okay. So like for like the formula of a normal alkane, we know that it should be something like CnH2n plus 2. And it's like normal to think about if you like, because each carbon you can see as like 2 hydrogen, and the one on the terminals has another one, so it's just plus 2. But like in this case, we found that this is CnH2n, and which means that 2 of the hydrogen are gone. And the 2 ways that can happen is, first you have a double bond, and like you lose 2 hydrogens. And the second way is that like the 2 terminals are connected and forming a ring, so that you lose the 2 hydrogen on the terminal. So like these are the 2 ways. So knowing that, we can draw the structure of these, like something like this, and double bonds, and like there's like cis and trans isomers, which could be like something like this. So like that's the structure is possible, I think. And like some of them contain CC double bond because like you need to lose 2 hydrogen, and we know that double bond is formed by a sigma bond and pi bond, and so sigma bond is formed by like 2 sp2 orbitals, and with like head to head, something like this. Yes, and pi bond is like formed by 2 p orbitals and shoulder to shoulder, something like this. Yeah, so like, but the more important orbital here is like the p orbital, because that's what makes the double bond special, since normal single bonds all have like sigma bond. And we just call them isomers. I think we already know that. So for like naming alkanes, we normally we just treat like the double bond like a functional group, and do the same thing with as if it's like a hydroxy group or other group. So for example, like this thing, if you draw, it should be something like this. Something like this. But like it's wrong because like the number could have been smaller. In this case, they're naming it like this. But what you can really do is like you just go from the opposite side. It's like 1 and 2. So which means it should be something like that's 2 SO and 1 pentane. Something like that. You think. And like in the next example, Venom is like the functional group that's directly connected to the double bond. So what they mean here is probably a propane with a double bond like this. But I don't think we use like Venom in this situation. What we do is just like you count the longest chain, which is propane, and you change the suffix from ANE to ENE because it's double bond, and there's like a second here.
Well, then, did you miss a carbon here? And the double bond is supposed to be here, right? Because this part is called the vinyl.
Oh, really?
This is my understanding.
Oh, okay.
Because you have a vinyl group on the central carbon. So if you have something like this, you cannot call this a vinyl group, right?
Oh, okay.
Yeah. Oh, one more thing about this example. So obviously the chain here is not the longest, right? Because longest actually is this one. But why we still choose this one is we want to have the double bond in the main chain. So our priority is to have the double bond, and then is the longest. So this is different from how we number the carbons in the alkane, because in that case there is no functional group, so we just pick up the longest one, right? So it's correct. Just a little bit more justification about why we choose this one. Okay, go ahead.
So like for a Lilith essay, like similarly, you first draw like an essay and like a Lilith group. Is it something like this? I'm not very sure.
A allelic is something like this. So the 3 carbons in this way with a double bond in the end is called allelic.
Yeah, so like this.
Yeah.
Okay. And like if we draw it like better, it should be something like this. And to name this, you like count the longest chain with double bond, which is like a pentane. So like just one pentane. Like basically you can imagine if this is like a hydroxy group and like number it in the same fashion, but change the suffix from ANE to ENE. Yes.
Oh, let me clean my stuff.
And like it could get like more complicated. Like in this example, you have like so many substituents on the both sides, so you cannot just say like it's cis or trans because there's more than 2 substituents. So that in this case, we need to assign what is called like E and Z. Wait, let me see. So like the way we E and Z works is that like across the double bond, we assign the groups with different priority. And if the 2 largest, or like the 2 most important groups are on the same side, they're called like this. They're called like Z, but like if they're on the opposite side, they're called E. So like, how do we know which one is more important? It's basically like steps listed below. So like you just like kind of count the atoms on the substituents, and the first time you encounter like an atom with a higher like greater atomic numbers, like so that means it's more important. So like let me see some examples here. So like in this case, if we are comparing these 2 groups, we know that this is a CH3. So the first one is a carbon, so it's like 12. And this is also 12, but like for CH3, you just kind of end there. There's nothing more. But in this case, there's another carbon. So that means this is more important. And because there's like only one substituent here, so this is, wait, what? I kind of messed up. You see. Yes, it's just compare these 2 groups. Let me do it again. Like, because on the left side, there's only one group, so that this is definitely the, like, if you compare with the hydrogen, carbon is 12, hydrogen is 1, so this is the more important one. And on the right side, we know that this is a carbon whose atomic number is like 12. This is also 12. So since they're the same, you move on to the next one. And if you move on to the next one, this is also 12 and 12, so still the same. And when we encounter double bonds, we see it as like it's connected 2 of the same atom. So the next one is like 212. But like for this one is also 212, but like for this one, you can only go on to here, which is connected to 2 hydrogen, and both are 1. But this is connected to 3 hydrogen, so like the top one should be more important. Thus, it should be C.
Wait a second. I disagree with you. So you analyze, in the end, this one and this one, right? So there are 3 hydrogens. There are only 2 hydrogens, but actually there is 1 more carbon connected to this carbon because the double bond is counted for twice for each carbon.
No, but like okay.
So which means this carbon has 3 carbons connected, actually. Carbon, carbon, carbon. So these 2 bonds are from the double bond. So we kind of separate double bond into CC single bond. So for the terminal carbon is also the same. So it carry 2 hydrogen and 1 carbon and another carbon. And this carbon is from the double bond. So we should argue, it's not because there are 3 hydrogens, which is, more important or more has a higher priority than 2 hydrogens. It should be this carbon actually has 2 hydrogens, but there's 2 carbons. So the bottom one is supposed to be, have a higher priority.
Yes. So like similarly on the right side, firstly it's just like these 2 are the same, so like you don't need to care about them. Why is the drawing not like updated? Can you see my like drawing on the screen?
No, right now.
Okay, I don't know what's happening. Use annotate for now. Like, so for these 2 carbon, they're like definitely the same because they're both like connect to another carbon and like 2 hydrogen. But for this one, it's like connected to additional carbon. So like you treat this as more important. So like it should be this side. And for this, these 2 are the same because they're both carbon, but the next one is, this one is hydrogen. I mean like oxygen, and it has a greater atomic number than the carbon. So like this one is more important. So after all, it should be Z. Like this. Do you have any questions?
Hey, sorry, can you repeat how do you determine the left side you use?
I'm sorry, what did you say?
I mean the left part, because it seems to me like the, because it's only the same thing. So why is this part, the upper part, more important?
Because like for this carbon is connected to hydrogen, but for this carbon it's like 1 CH3 and another hydrogen. Like because it's connected to another carbon and that's like larger than the hydrogen, so this is like more important. So like the upper part overall is like more important.
So you kind of assume there's a line that divided between the middle instead of calculating the whole part.
Yeah, kind of like that. And like, yeah.
Okay, I see. Thanks.
Okay. So next, wait.
Can you summarize, the ZE again? So what is called Z? What is called E?
Z is when you have like the, for example, if I draw this. If you have like R1 has higher priority than R3 and R2 has higher priority than R4, we call this Z because they're on the like same side of the double bond. And if the opposite happens, when they're like on the opposite sides, we call them E, which
So
sounds a lot like the E in
Z
Chinese.
is similar to trans. To cis, and E is similar to trans, right?
Yes.
Okay.
Why is the share screen not working? Let me share again.
Yeah, sometimes the high technology needs a longer time to respond.
Okay. So this is like p orbitals because you use p orbitals to form pi bonds. And for the next question, we can first analysis from like the dipole perspective. We know that Br is very electronegative, so there should be like a lot of electron here, but here is like kind of electron positive. And for the alkane, since there's like one more bond, the pi bond, so that like, here is pretty electron rich. So what happens is the electron rich part kind of attacks the hydrogen and leaving the bromide, which gives us something like this. H, a positive charge plus Br minus. And since the one is like positive, the other is negative, so it's kind of natural for them just to like bind together and gives us something like this. Yeah, it's pretty straightforward. And like for here, since like the two sides are not symmetric, there could be two positive intermediate, which one is when you add hydrogen here and a positive charge here. The other is like the opposite, something like this. So only one product is formed. So like one of the intermediate is known to be stabler than the other. And like I think it's discussed later. Let me see. Yes, here. So why is the like carbon cation connected to more carbons are more stable than the one connected to hydrogen? It's like the similar idea why ethanol is less acidic than like water. So the thing is like like carbon is more electron donating than hydrogen, so that is the more carbon is connected to the carbon cation is going to stabilize it more. Like, does that make sense?
William, though, you know, tert butoxide is more acidic than ethanol in gas phase. If you remember that question.
Oh yeah, that's your question.
Yeah, that is a different story. So we are talking about the aqueous system right now.
Yeah, possibly like ethanol can be like a subject to solvent effect as well.
Yeah, the size is smaller, so it has a better solvation. So what I want to add one more point is, William just mentioned about the brief reason why the tertiary. First, let's re-emphasize a few terminologies. This one is called a tertiary carbocation. Is it like this? Not sure. TIRTIARY. This is called a secondary. This is called a primary.
Doctor, I think TER.
TIA. Am I right?
Yes.
Okay, good. And this one is the 0 level, right? 0 level. So how we define the 1, 2, 3 is based on how many carbons are connected to the carbon with the positive charge. So this makes sense to you, right? And the simple explanation why tertiary is more stable than secondary than primary is because the methyl group or the alkyl group, they are electron donating. So basically R is electron pushing or electron donating, so which will stabilize the carbocation. So let's first accept this. But how to explain why R is electron donating? This is something called hyperconjugation. What is hyperconjugation? So let's try to draw it. So this is the central carbon, is sp2 hybridized. It has a empty p orbital with a positive charge. So at the same time, there are 3 carbons connected. So each carbon is sp3 hybridized, right? So now we can see the angle here. This is the bad color. The angle here is 90. The angle here is 109.5 or around 109.5. Am I right? So basically, we know the CH bond is also made by a sp3 hybridization, right? This is the sp3 hybridized, orbital. So now we think there is a kind of, limited overlap between this lobe with this lobe, because actually they are not so far away from each other, right? So the overlap is very limited because first, the 2 orbitals are not fully parallel to each other, right? One is 90, another one is 109.5. So it's like this. So one is perpendicular, another one is a little bit, italic. So which makes the overlap relatively limited. This is the first reason. The second reason is these two orbitals, they do not have the same size as well, right? So the lone pair on the carbon probably is different from the size with the sp3 hybridized bond in the CH bond. This is the second limitation. And third one is, if we have two p orbitals to overlap in this way, they will overlap both in the top and in the bottom, right? But here, obviously, the bottom parts pretty much has no overlap because this is determined by the shape of the sp3 hybridized orbital, one large lobe and another small lobe. So this is why it's called hyperconjugation. It still have the conjugation. This kind of overlap is called conjugation, but the hyper here means super weak. But this kind of super weak conjugation still works because there are two electrons here. So these two electrons can help to stabilize the empty p orbital, which will make the carbocation more positive. So think about, if there are more CH bond or CC bond connected, there will be more chance to have this kind of hyperconjugation, because we know this bond can be freely rotated. So you got more chances to have the hyperconjugation. But if in another case, there is a hydrogen connected, think about, is there still any hyperconjugation? So there's no hyperconjugation at all, right? Because the bond is here. So there's no similar bond in this way to kind of, partially or weakly overlap with the p orbital. So this is called hyperconjugation. So it's a little bit, complicated. So this is the strategy used to explain why typically a R group is electron pushing or electron donating. Does this make sense to you? Well, would you mind to turn back to the previous slides? Just want to double check. So based on this, William, which one will be the major products here?
It should be this one because the carbocation is more stabilized.
I think now is the time for you to briefly summarize the M rule, right? The Markovnikov rule.
Sure.
Mm-hmm. I can clean my stuff.
Yeah.
Okay.
So like for a random unsymmetric alkane, for example, like this, and if you use like addition reaction, like the reaction is going to go in a way that the intermediate is more stable, which means that the carbocation needs to be placed in the more substitute side than like compared to the less substitute because of hyperconjugation, and which means that the bromine will be added at the more substitute side. So like that's basically the M rule, because like which is for addition reactions, the halide usually adds to the more substitute side of the alkane, while the hydrogen adds to the like less substitute.
Just a little bit background about the rule. How to spell the name? Markov.
K-O-V. No L. No L.
M-A-R. Kov. Ni.
Kov. K-O-V. Yep.
Okay. Yang, what is the right way to pronounce this word?
Markovnikov, but whatever. Who cares?
Markovnikov. I like it. It sounds Russian. What is how to pronounce Putin's name in Russian? Just Putin?
No idea.
Oh, his first name is, what is Putin's first name? Dmitry?
Vladimir.
No, Vladimir.
Vladimir.
Dmitry is the first name of Mendeleev.
Who?
Mendeleev, Dmitry,
and also
Dmitry.
I think Medvedev, like
Okay.
yeah,
Okay.
Dmitry Medvedev. I think.
So what I want to say is, this Russian scientist, he originally summarized. So the hydrogen will be added to the carbon in the alkene with more hydrogens. Basically here, one hydrogen, no hydrogen, zero hydrogen, here, one hydrogen. So he mentioned about if the alkene does a addition reaction, the hydrogen will be added to the sides with more hydrogen connected. This is his original summary. But you probably see there are a few limitations. The first, he didn't explain why it's like this, because at that time, we are not sure what is the mechanism. He summarized this pretty early. Secondly, if we do not add HBr, let's say we add a Br2, we'll add something like others with no hydrogen. So his rule doesn't work anymore, right? Because we don't know how to, choose the major products. So later, actually based on William's discussion, so the stability of the carbocation is the main reason behind this. And another thing is, let me see, A, B. Yeah, that's it. Yeah, this is called M rule, the Markovnikov rule. Yeah, there might be a few exceptions. We'll discuss, after we finish everything. But and the last piece. So both of these two carbocations intermediates are produced, but just because the left one is more stable than the right one. So this one will be the major intermediate. This one will be the minor. So you will get both products, but just the one, formed by the major carbocation will be the major products. So basically this one will be the major products. This one will be the minor products, right? William, do you have any other stuff to add?
Not really.
Good. Yeah, how do you think about William's teaching?
Very strong.
Terrible.
A round of applause to William. It's phenomenal. I like it. Thank you, William. I think William set up a pretty high bar, right? While we're seniors.